Now the fun part, making sure that all of this hard work ends up with a wonderful, strong, sturdy, geometric wall that is going to both be functional and have the form of a perfect rectangle. Now, the trouble is before we go and cut and put on a wall, is making sure that this is a perfect rectangle with 4 90-degree angle corners. The issue with something like this is if we were to turn it, it is very easy to turn this into a parallelogram either way. This is what's referred to as racking. And if we have something like this, it's going to have unequal forces being applied, and over time turning that into a parallelogram. And the reason we don't want that is because that's taking away the structure and the stability of that wall. If everything is 90 degrees, when a load is applied here, that wall is going to withstand that load at its peak performance. If it's off by a degree and that load is constantly bearing down, over time, the structure and the integrity of that wall is going to be, it's going to be bad over time, right? The integrity of it is going to degrade. And we could obviously think about the millions of applications, but nothing more simple than just the wall in your house. If it's out of 90 degrees, that's going to cause a lot of problems over time. So, insert math. The math that is involved in this, probably one of the most practical uses of a very fancy formula, is making sure that something such as a wall, a floor, anything actually is perfectly square. And when I mean square, 90 degrees. And that is Pythagorean theorem. Pythagorean theorem states that if you have a right triangle, so here's the 90 degrees, the legs of the right triangle have a relationship with what's referred to as the hypotenuse. And the hypotenuse is here, C. So C is the hypotenuse. So the legs of the right triangle, which are A and B, have a relationship with the length of the hypotenuse. And if we know what the hypotenuse is, we can make sure that A and B are perfectly 90 degrees. That is used probably more often on construction sites than any other math aside from simple measuring. And obviously a rectangle or square is just 2 triangles. So if we were to take this triangle and replicate it here with a 90 degree, that shared hypotenuse of the 2 triangles would ensure that we have a perfect square, and thus 90 degrees in all 4 corners of the square or rectangle, depending on the size of A and B. And Pythagorean theorem, again, simple formula. It's A squared, so take the value of A and square it, the value of B and square it, and that is equal to C squared. So we have A squared plus B squared equals C squared, and it's just a matter of substituting in the value for A, substituting in the value for B. Once you know those, you measure them, and you can find C to ensure you have a perfect 90 degrees. A lot of people rewrite this formula to simplify it, much like we simplify fractions so that it's easier to use. And common in math practice is how we isolate the variable C without it being squared is we find the square root. And what we do to one side, we do to the other side. So if we were to find the square root of C, we would square root this side as well. And the formula is often expressed or simplified as the square root of A squared plus B squared is equal to C. And if you were to go online to something like Google, you would often see this as the formula expressed, as opposed to a squared plus b squared equals c squared. And it's, again, just a simplification. So we're going to see the application of Pythagorean theorem to ensure our wall has 4 90-degree corners. Okay, now to find essentially what the hypotenuse should be. In other words, what the distance from this corner to this corner should be. And if I have this perfectly measured out, then I know that I'm going to have 4 90-degree angles as opposed to not having a 90-degree angles in each corner. So, math and where math plays into this. In order to find the measurement of the hypotenuse, I need to first find the measurement of, well, what each leg of the right angle should be. I'm just going to draw a quick picture, and I'm going to have my wall here, okay? And I'm going to start in the bottom left, kind of as if you would be the origin. And you want to make sure that you're measuring from the outside to the outside. So we're going to find this one, and that's going to be called A, and then the outside to the outside, and that's B. Whatever measuring you're doing, whether that's with a tape measure or ruler, whatever, I'm using my grid and my cutting mat because it has measurements on that. You want to make sure that you measure once, twice, 3 times, 4 times, whatever that you need to do to make sure that you are being as precise as possible. So I found my A to be 4 3/4 inches. Again, I'm using inches. So whatever that might be for you, maybe you're using centimeters, which I would highly recommend. Again, reason why I'm not is because of my cutting mat being in inches. So I found A to equal 4 3/4 inch, and I found B to equal 10 5/8 inch. Now, the problem here for a lot of people is these wonderful things called fractions. And this is probably the biggest application of math that I use inside a workshop or on a construction site all the time, is when I'm using fractions. My brain isn't a big fan of fractions unless it's half, quarter, or 3/4. Any other fraction I'm not a huge fan of. So I often use the conversion and knowledge that fractions are decimals because I find decimals easier to use. So for example, 4 3/4 is the same thing as saying 4.75 because I know 3/4 is 0.75 or 75% of 1 inch. And the same thing can be done for 5/8. And because 5/8 is a very common fraction that I use, I know off the top of my head that that is 10.625. But a great strategy is, how do I convert this fraction to a decimal? It's just straight division. 5/8 is the same thing as 5 divided by 8. And if I do that math, 5 divided by 8, whether you're using a calculator, whether you're using long division, you'll find out that 5/8 is equivalent to 0.625. So another great math application, and why that's used and why we have to learn it and why we need to understand it, the knowledge of understanding that fractions are decimals and are percents. So something as simple as 3/4 is equal to 0.75, which is also equal to 75%. Being able to understand that this is something and knowledge that exists in the world can be used on an everyday basis, such as constructing a wall by a carpenter or a framer or a student making a cardboard wall. Okay, so Pythagorean theorem in action. We've converted 2 decimals last time and written out the formula, and I color-coded it for you guys so that you can see the process of substituting and isolating variables and solving for that which is isolating c. So we have a squared plus b squared equals c squared. I substituted in the value, so I know that a is equal to 4.75. So I substituted that in for a. B is equal to 10.625, which is that 5/8. Substituted that in for B, and I've left C because that's the variable I want to know. So essentially I've gotten rid of the letter A, gotten rid of the letter B, and left the letter that I want to solve for. Much like when we find the area of a triangle, we can find A area is equal to length times width. We leave A because we want to know what the area is, and we don't know that yet. It's the unknown variable. But we substitute in what we do know as the length and the width, do the math, and out comes our area. Same thing, same skill. So we squared 4.75, so that's 4.75 times 4.75, which leaves us with 22.5625. We took 10.625, squared that. Again, it's multiplying it by itself, not by 2, which leaves us with 112.890625. And we are adding these up together results in 135.453125. You will notice that there are a lot of decimals. I didn't do any rounding whatsoever, because by rounding here, you're going to throw off your final number, and you want to be as precise as possible. Now, we are left with c squared, and we want to get rid of that squared. So in order to eliminate that squared, we square root both sides. So what we're doing here is we're square rooting the c to get rid of the 2, and what we do to one side of the equation, we also have to do to the other. That is why we have the square root of 135.453125 is equal to c, and that is equal to 11.63. This is rounded here, so we've eliminated and we've gone to 2 decimal spots. And we already know that decimal 625 is equivalent to 5/8. And the reason I rounded here is because my tape measure, so my measurement only uses eighths, and I can't round up to the next full eighth because the next full eighths would be 3/4, which is 7/5. So I know that it is 11 and 5/8, which is 625, and I put the plus here because it's essentially a 16th plus 5/8. So 16th plus would actually be 11/16. So really what I'm saying here in construction terms is 11 and 5/8 heavy, which means I'm a 16th over, but my tape measure doesn't go and use 16ths. So to apply that, now that I have that number, I'm going to see if my wall is square. So what I did is I took a straight edge and I simply measured the distance from this end to this end as 11 and 5/8 heavy. And what I do is I start in one corner, making sure it's outside to outside. And what I can do is, see how I'm turning from racking, is that should represent the distance from one corner to the other. And as you can tell, it's pretty much bang on. And you can measure that from both sides, again, making sure you're outside to outside, and you'll be able to identify that. And where this does come into play is when we are cutting out our rectangle. So most of us would probably just want to go, yeah, I'm just going to put it on, I'm going to trace it, but as you trace it, it moves and it does a bunch of different things. So what we can do is we can make sure that if we start with a perfect 90-degree corner, and to do that I used my cutting mat, I measured out my 10 and 5/8, I measured up my 4 3/4, and then I can take my mark and make sure, and as you can see here, again going outside to outside, so there's my point there at 4 3/4, point there, and you can see that using Pythagorean theorem, I now know that this is absolutely perfect and square. And before I cut this out, I now know that I have 4 perfect right angles. And then if I cut this out and then put it onto here and make sure that my corners are all aligned perfectly, I'm going to have a wonderfully square and perfect wall. Okay, a couple of pointers, tips, and tricks. Making sure that once you've cut out your piece using math, okay, again, not using estimations and tracing, using math, cutting it out, I now take the time to make sure that each corner is 90 degrees, and you can tell by the lines, I've taken my time, made sure that each corner is very, very 90 degrees. I've used math, I've gone over, double checked things. The last thing you want to think about is the structure of the cardboard. And again, going back to those flutes, we want the strength of the flutes to help our wall. It's adding another cylinder or column, I shouldn't say cylinder, another column of strength to that wall. And what we're going to do is make sure that we have the wall and the frame of the wall in line with the flutes, just like we did with our hockey sticks. You can see that I can't see any of those perforations this way. It's because all my flutes are traveling in the same direction. The obvious ones that aren't doing that are the top and the bottom, but that's okay for this because the structure that they're holding up is all the flutes. Now the simple process is to glue this piece to this piece, or realistically glue this piece to this. Now, because I'm using my diaper box, I didn't want this on the outside. I'm going to face that to the inside and have my finished wall as a piece of cardboard, which is a lot more blank. What I would recommend for this is a couple of things. You can definitely go around the outside with your glue gun and glue, 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 put a bunch. When you do that, you are going to have quite a bit of squeeze outs. It'll be a bit messy because there's a lot of cavities and such. So what you might want to do is try to glue this piece to this, in which case you'll just run glue along this piece of the cardboard and then stick it on. But strategy is completely up to you. The important part is that when you do glue it on, you're making sure that all the edges are perfectly flush. Okay, you will notice there's a bit of a curve here with this, but both edges, when they line up, are perfectly flush. So this edge is lining up with the bottom piece, and this edge is lining up here. The right angle is actually what we want because of the way we built this. It's curved and not a right angle. So once you do that, you will have a wall that is pretty darn sturdy. So go ahead and do that.